Hello, my name is Nick Clark, and I'm an ARC Decker Fellow based at the University of Queensland in Australia. And today I'm going to talk to you about a set of methods and an associated R package that I'm developing to fit dynamic generalized additive models and use them for forecasting. But before I start, I'd like to just briefly acknowledge the traditional owners of the land in which I'm working, the Turrbal and Yugira people. Okay, so I won't spend much time talking about the background of GAMs. Essentially, you can think of them as modified generalized linear models, where some or all of those linear additive effects are replaced by smooth nonlinear functions. Each of these functions is penalized to enforce smoothness, which is useful for guarding against overfitting. But again, if you're interested in learning more about GAMs, the theory of GAMs and the way that they're estimated, I encourage you to have a look at this webinar by Dr. Kevin Simpson that was given to EFI a year ago, and some of his other associated materials. But again, just visually, it's useful to be able to see how smooth functions actually work. So here, each of these colored regions shows a different basis function, and these briefly or mildly overlapping basis functions altogether make up the overall smooth function. And each of those basis functions can get a different weight or coefficient that has to be estimated that altogether controls the shape and smoothness of the function. So they're very, very flexible. And the penalty helps to, again, enforce smoothness, which is useful when you have noisy data and you don't want your spline to overfit. A very important property of GAMs is that we can also use partial pooling to estimate hierarchical effects, just like we can with a standard hierarchical linear model. And this is very important when we have time series, especially, that we expect to show some kind of dependencies, which is very common in ecology. So we can actually partially pool the shapes and the smoothness parameters of these functions, which allows us to generalize our models to other time series that we haven't observed yet, and also to make better inferences for noisy data. Okay, so it's not surprising that GAMs are very widely used in ecology, which is great and wonderful. I'm sure a lot of the audience has used them yourselves. But a property that I'd like to point your attention to with these smoothing splines is the fact that they're not designed to extrapolate beyond the training data. So here I have two different smooth splines that were fit to time for a particular simulated time series. You can see both of these splines. The first one uses the standard second derivative penalty, and the one at the bottom uses the first derivative penalty. And they both have very different properties for how they extrapolate beyond the training data, but neither of these extrapolations is actually very useful for forecasting. So in the second derivative case, which is the most common, that extrapolation will go on linearly into the future. The uncertainty will grow a bit, but it won't grow in a principled way that actually has some understanding of time. The first derivative penalty will actually go in a straight line with no increase in uncertainty. So neither of these, again, is very useful if we want to make good forecasts. So it's very tempting to fit a smooth function to time when you're estimating time series, and maybe that's good for inference on that time series. But if your goal is forecasting, then just beware that you can have very strange behaviors. So I recognize this because I like to use GAMs in my work, but I wanted to use them for forecasting. And so I've been working on an R package and a set of methods that augments the linear predictor of a GAM with a latent temporal trend. In the simplest case, this latent trend is just a random walk, which can be estimated for each different time series if we have a set of time series. Or we can estimate more complex trends, autoregressive processes, and even Gaussian processes are in the pipeline at the moment. And importantly, we can estimate those independently for each time series or jointly if we have a set of time series that we think show some temporal dependencies. And I'll just very briefly highlight what I mean by that when we talk about temporal dependencies. If we assume we have a set of time series here that are each of these colored lines, there can be some dependencies here, but it might not be obvious just by looking at them or by estimating cross correlations. And so a very useful type of model that's commonly used for dimension reduction in other types of forecasting is a dynamic factor model. And so here we're estimating a single dynamic factor, which is the black line there. And the loading coefficients of each of those series controls their dependencies on that latent factor. And by proxy, that helps to induce correlations among those series if there's evidence for those correlations to exist. Okay, so these loading factors are really useful for for capturing types of associations as well as very complex associations, especially if we estimate multiple dynamic factors in a single model. They can be tricky to estimate, of course, so we have to use quite strong priors to induce informative estimates. But anyway, this is a very useful type of property that's available in the package that I'm working on, and I'm hoping to improve those going forward. Okay, so I have fit some simulations using these types of GAMs and compared them to standard GAMs, and they tend to perform much better in forecasting exercises. I won't talk about that here because I want to just very briefly highlight actual forecasting tasks where I've used these types of models to show their properties and how useful they can be. So I applied dynamic GAMs to the time series from Neon for tick abundances. These are our nymph tick abundances, which is one of the Neon forecasting challenges. If you've worked with these data, you know that they have many statistical challenges. They're discrete, highly over-dispersed, and very high proportion of missingness, and also many zeros, some of which are true and some of which might not be true. Okay, so generalized linear models are an obvious choice to try and estimate these, but if we want to generate forecasts, then we need some kind of dynamic component. Dynamic GAMs are a good way to be able to do that. So I fit dynamic GAMs to some of these series just to see how the models performed and how we might use them in a principled way to improve our understanding of inference and forecasts. And again, just highlighting some of the results so you can see what kinds of outputs we can get from these models. Here we have smooth functions estimated for a repeated cyclic seasonality for one of these time series, a smooth, slightly nonlinear function for an effect of a covariate. And you can see the forecast here, which is quite sensible. This was a random walk latent temporal process for this series. We're also able to use, because this is a Bayesian model, we can use posterior retrodictive checks and posterior predictive checks. And both of these show really quite good fit to the data so that the model is able to simulate time series that look and resemble the properties of the actual observed data. Okay, so there's a preprint available describing these models and the associated R package. So you're welcome to view that, and I would encourage you to. But if you're interested in this kind of model, then looking at my GitHub account, you'll be able to see the most up-to-date version of the R package and what I'm working on there. So currently this is all estimated in software JAGS, but I am implementing features to be able to estimate using Hamiltonian Monte Carlo in STAN, which will be nice for offering more utility. So thank you all very much. I really appreciate your time, and I'm happy to take any questions.